So as Donkey mentioned, for our next talk, we have actually a speaker pair. We have David and Angeline. Now, David and Angeline both are a long-time thought workers. Both are brilliant engineers, and both love everything about data. They both have experience working on data projects with the various clients across the various domains. Now, in today's talk, what they are going to talk about is the challenges that you normally face on a data project when it comes to implementing those engineering practices. And of course, they're going to share some of the techniques which you can use to overcome those challenges. So without any further ado, I'll just hand over to those lovely speakers, David and Angeline. Over to you, folks.
Hello. Thank you, Harshal.
Hi, everyone. I'm Angeline and he's David. In this talk, we will be covering 4 challenges which we've observed to be common in data projects that we've been on, and how they could be addressed with proper engineering practices.
Yeah, we call them enduring engineering practices because these are practices that have endured years and maybe even decades in agile software projects and are critical to success of these projects. So today we'll share how you can apply them to solve some of the problems that we regularly face in data projects.
Thank you, David. Okay, so to walk us through these 4 challenges, let us first start with a story. This is a story about a data project and a data science team. And let me jump right into it. So let's meet Dana. Dana is a data scientist at Best Price. Best Price is a major groceries company. Best Price is a 10-year-old company, and it rose to success overnight last year due to trends towards online grocery shopping. Best Price has an existing monolithic web application. They have data stored in a monolithic transactional database, for example, like Microsoft SQL Server. The machine learning use case in this study goes as follows. The CTO of Best Price is trying to get a new round of funding for the company. And because of this, he would like Dana and her team of data scientists to develop a machine learning powered recommender system. And the purpose of the system is to get customers to add more products to their shopping cart and hence increase the sales of the company. Okay, so we're off to a great start. Dana and her team spent a few months, and what they've done is they've gathered business requirements. They've also managed to train a prototype recommendation model. Next, they have also validated that this model could be used to resolve business needs. And finally, they ended up with a ML model prototype that is successfully trained and can make intelligent product recommendations on their website. Dana and her team are really glad, and they would like to now pass this model to the development team to deploy to production. Now, could this be done?
Unfortunately, in our scenario, no. And even though the ML proof of concept was great, we couldn't productionize this model for 2 reasons. One is that the data was mired in a monolithic relational database. And while they had kind of did a one-time batch dump to train the models, this transactional system cannot support the machine learning model's analytical workload. And the second thing is that the model performance is kind of decent, but it could improve with some more additional features. But these features do not yet exist. So we need to collect some more data before we can have a good enough model to deploy to production. And therein lies the first challenge of our data project. And the challenge is that we can't just do ML without first laying some foundational groundwork. And this is a recurring theme that we've seen across several projects that we've observed. And many ML projects start as promising proof of concepts, but we simply cannot stand them up in production because the models do not have the data engineering foundation to stand on to make decisions. And even if we find the resources within our organization to lay the data engineering groundwork, laying just the right amount of groundwork is a challenge in itself, and that we've seen many organizations face. On the one hand, we've seen organizations that build too much, right? Organizations can spend months and years collecting all sorts of data, building all sorts of big data tooling to solve big data problems. However, we typically hit a bottleneck when we try to deliver insight and value out of the data that we have. And this is often because it's easy to get into the trap of collecting data for the sake of collecting data and not starting with the end in mind, which is to create a data-driven product that delivers customer value. And on the other hand, we can build not enough, we can build too little. Data scientists and data teams are left on their own to bash their own path, pun intended, to bash their own path through transactional systems to bootstrap data that they need for machine learning. And that is why many ML projects end up in the graveyard of concepts. And because there's not enough tools or tooling to enable data scientists to do what they need to do or what they're good at, to train models, to deploy models, they often get stuck. They are stuck at the proof of concept stage. The organizational infra is just not enough to help them be awesome. And so this is where many data scientists burn out and even leave the organization. So what can we do about it? If our recommendation can be summed up in 2 words, it would be data mesh. And the general idea of data mesh is to iteratively grow our data platform by taking on one vertical slice at a time.
That sounds interesting, David. Could you let us know what exactly is a data mesh and how can a data mesh be used to resolve the issue that we see here?
So data mesh is an upcoming topic. It's been around for maybe 2 years, I guess. It's an emerging topic. There's a lot of great content, great books, videos, articles on it. So we will share some links at the end of our talk on it. But in gist, I'll try to summarize in the slide. The approach of data mesh is, it recommends that we vertically slice our data architecture so that we can enable autonomous product teams to autonomously create and consume data products. So then teams can iterate on these products and deliver customer value without depending on a centralized data team, which can tend to be a bottleneck. And they can do this using the tools and abstractions provided by the platform that we built. So in Dana's example, we might learn that even though the relational DB is big, and if you in your mind can imagine like 40 tables, a crazy ERD database diagram, and one table might have like 30 columns, right? So over 10 years, our core transactional system can evolve in weird and wonderful ways. But in Dana's team, we might learn that we only need sales-related data, the green column on the left. So from there, we can vertically slice and start creating a data platform to start smuggling out transactional data out of just the sales-related tables and put it into an analytical data layer that can serve production workloads, analytical workloads, something like Google BigQuery or Amazon Redshift. And this can then be used to power the ML product. And as a bonus, not just this product, there can be other products that we start to get ideas for once we have this data access layer. So you could have reporting, insights, any other kind of data powered products. So once these products have been curated and created, they can be used by any other teams on a self-service basis. So again, it is a big topic. I can't cover everything in one slide. So we'll share the links for you to read more and watch more about at the end of the talk. So in Dana's team, now we've worked a few months and we've now came up with a vertically sliced, thinnest viable data platform. And we've been operating this data platform and data pipelines for some months now. Data has been streaming in, and the Dana's team has been able to train and deploy the recommendation model. So are we all good now?
Not really, David. So data platforms are not a silver bullet, and complexity can easily get out of hand if we don't manage it with good engineering practices. So let me illustrate further. All right, back to our story with Dana. So we've got a data platform now that's thinly sliced and built with the best practices that David recommended earlier. After a few months, where Dana's team developed this thin slice data platform, what this platform can do is that it ingests the latest data daily from the transactional systems. And what it does is it saves the data to a central data lake. And from there, the recommender model is trained with data from this data lake. And all pipelines are working functionally fine. However, what we see now is that entropy starts to set in. And what I meant by that is that due to a lack of test automation in this data platform, it caused a huge manual regression testing effort required by the QA team of the company every time a new change was required to be made in this data system. As the data pipeline could not be run locally, developers also had to deploy code often to the SIT environment, and they have to do this iteratively to figure out if the code they've just written works. And all the above issues led to slow and error-prone releases every 2 months instead of every 2 weeks as planned. So what we see here is the team had chosen a data platform that works well churning the data. However, this platform did not come with good engineering sensible defaults. So in summary, what I meant is these problems cause a long feedback cycle to happen. Okay, next slide, please. And now I'll come to challenge 2, where data platform tooling does not always include agile sensible defaults. And what I meant by that is that because data projects typically involve a mismatch of different frameworks, due to a lack of a standardized way of building a data pipeline, there is also a lack of a standardized way to test it automatically. Unlike its more mature counterparts, for example, like API testing frameworks or front-end UI testing frameworks, where you can get out-of-the-box testing solutions in a jiffy. We cannot do the same for data projects, unfortunately. So to summarize what happened here in the problem is that the lack of test automation led to unscalable manual regression testing effort to be done. And this caused hair tearing and slow release process. Okay. Next slide, please. Okay. So how can we resolve that? We would like to recommend that the team apply some of traditional software engineering sensible defaults, but to their data projects, because many of these problems are already solved problems. So in Dana's example, what could speed up the release process could be using a continuous integration pipeline, and this could be set up so that we have automated deployment of code into different environments. Okay? And we could also use the concept of infrastructure as code by making use of Terraform scripts to automate the provisioning of environments. And this would lead to repeatable as well as identical environments, which all behave in the same way. For faster feedback, developers, instead of waiting for code to be deployed before they know if it works, they could make use of Docker to spin up a local environment so that they do not have to deploy their code to know if it works. They could run it locally and to ensure that it's working. And lastly, we could use the test pyramid and ensure that tests are available on different layers. Developers can work on unit and integration tests, while quality analysts in the team can work on end-to-end journey tests. And this will ensure that automated tests are available at every level so that no regression bugs can creep in.
Yeah,
Okay,
thank you,
next slide,
Angeline.
please.
Yeah.
Thank you.
So thank you. Angeline has covered a few of the kind of sensible defaults on the path to production, testing on your CI and all your environments. In addition, this entropy can also plague us at the level of the code and the deployable, the thing that we're deploying itself. And this challenge plagues us partly because of myth, and that's the myth you see on the screen, which is that engineering practices are only for software engineers. The truth is, whether we like it or not, we are writing code on a data project. Whether you're a data scientist, a data engineer, we're all writing code. And because we're writing code, there is a set of time-tested practices, and Angeline has covered a few of them. There are these time-tested practices from the software engineering world. To be specific, the agile software engineering world that can help us solve this problem. So first, let me describe the problem and I'll share our recommendations. So the main problem is entropy, as Angeline mentioned. And I put here data in brackets because the truth is entropy is everywhere, not just in data projects. It's the law of the universe. Everything tends towards chaos and often more quickly than we expect. So it can manifest itself in one level, which is a level of the code. So it's very, in Dana's team, we eventually grew to have, a single Python script that is like 300 lines, 400 lines of code, no functions, no abstraction, 0 unit tests. And because this script was the thing that works, and people were afraid to change it because every time you change something, there was a very long feedback cycle. You're going to rerun everything, check the whole output, and validate, whether it's improved or got worse. And because it's kind of so scary to change it, people have a fear of refactoring. And without refactoring, we kind of just copy paste, and now we have 5 different versions of the same Python script instead of a single code base that we work together. So the code now starts to actively work against the team rather than for the team. And we'll share some mitigation measures shortly, but I also want to talk about another level of entropy, which is about at the dependency management level. So in Dana's team, we had the sandbox problem. We had a star developer, data scientist, who kind of made everything work. It works on his machine or her machine. But the moment we try to share this with a colleague, it goes red because she was using Python 3.2 and somebody else was using Python 3.9, something like that, right? And the moment we try to deploy this and on the CI, it blows up because some other dependency was not found. So you get the gist of it, and this is more common than you might think in data projects. And so what can we do about this, right? The good news is that there are a set of engineering practices that can help us manage entropy. And more frequently, you hear this term called MLOps, and it refers to a collection of capabilities such as CI/CD, automated testing, refactoring, containerization technology. How do we automate our infrastructure? And of course, machine learning and data engineering. However, it is clearly unreasonable to expect any one person to know all of these things. And in the old world of software development, we used to solve this problem by having functionally sliced teams, like a team of developers who are really good at writing code, a team of operations who really know Kubernetes and all of the operation things, right? But this had problems of its own. And this is what the DevOps movement tries to solve, in that we build cross-functional teams that work together. We build it, we run it, and this is what is kind of a sensible default in software teams now. And if you look at the diagram on the left-hand side, and if you replace the word developers with data scientists, and replace, let's say, testers with developers, you kind of see this is the operating model that many organizations use. And this is kind of the source of the problem, right? So our recommendation is that we develop enduring engineering capabilities by building cross-functional teams. Because I've personally seen teams that have great desire and great gusto to say, okay, we should do TDD. But the truth is, to learn it from scratch without this specialist or somebody who have experience in the team, it is very hard, right? So by embedding or flying in somebody who has that experience, maybe these two guys know, test automation, and these folks really know data science, and somebody really knows operations. As a team, we bring in all the capabilities on the left-hand side. We build it, we run it, and we kind of go to prod from day one, rather than spend 3 months doing a proof of concept and then struggle to productionize it later. So, of course, the specific team shape and resourcing will differ for each organization, but it is something to bear in mind as you try to set your team up for success. What do you think, Angeline?
Hi, David. I would like to add on that I totally agree with all your points. And I also like to say that I feel that your recommendation does not only affect the developers or the data scientists in the team, but even the quality analysts who are in charge of testing the whole end-to-end flow of the data pipeline. I feel that there's also a need for them to share with the other two departments domain knowledge to ensure that everyone can be on the same page and to get their job done effectively. For example, what I mean by that is that, for example, if a QA needs to test a feature involving a distributed system, then they would also need to know some basics of how distributed system works. So I feel that the lines are blurring between the different roles and what each role needs to know. Hence, I feel that everyone should try to have a positive kind of growth mindset and be willing to learn new things.
Yeah, thank you, Angeline. So growth mindset, right? This phrase comes from an excellent book by Carol Dweck. The book is called Mindset. And the premise of the book is that no one can do everything, nor should we try to do everything. But anyone can do anything with the right mindset, the right support structures, and with deliberate practice. So coming back to data projects, there are resources that can give data scientists pathways to learn the sensible defaults that we've been talking about in this talk: automated testing, refactoring, continuous integration, Dockerization. So again, whether we like it or not, we are writing code, and these practices can help us be more effective in the way we write code. By helping us, instead of manual testing, we have an automated test that runs in, seconds rather than, minutes or hours debugging some long code. All in all, this helps us to reduce mental overhead, automate repetitive tasks, so that we kind of are freed up to solve higher level problems, the things that we really want to do, rather than the low level, repetitive, annoying things that we have to do. In general, make life easier. So these are some of the resources that you can check out. We'll link them in the Slack channel as well. There's a repository called Clean Code ML, and from there you can get a link to a self-promotion here. This article that I wrote with the help of my colleagues. So these are everything that we talk about here. There are specific kind of implementation paths that you can follow and check out. So coming back to the story, we have our thin slice startup platform. We have improved our engineering practices, so we have all the good things that Angeline and I just described. Everything is good now, right?
Well, not really, David. And this leads us now to challenge 3. Yep. Thank you, David. Okay, so back to our story about Dana and her data science team. Something happened in production. In production, a customer noticed that the recommender system on their grocery website was giving random results. It was Valentine's Day, but as flowers were sold out, the system recommended to a customer to get chili peppers instead. The customer on the site felt that the situation was really funny, and he took a screenshot of the page and posted it online as a joke. Dana's boss, the CTO of Best Price, got wind of this, and he did not find the situation amusing at all. He called up Dana and her team and he would like them to figure out and give him an explanation on what happened. So what exactly happened here? Dana and her team had a stressful time debugging, but they managed to trace the issue back to some invalid data that was not detected, and this data was used to train the recommender model. Due to this, it resulted in a drop in the ML model accuracy of the recommender and led to the embarrassing situation for the company. Okay. So to dig deeper in this issue, what we can see here is that is it enough to test the code logic of a data pipeline? And in my opinion, the answer is no, because in a traditional system, testing is done to ensure that the code logic has no bugs and is good to go and be deployed. However, in a data system, the data is also part of the logic, because the data is used later to train a model which makes decisions for the business. Hence, due to this understanding, the data quality and integrity of this data matters a lot. It matters as much as the code. So what can we do to fix this issue? Okay, the solution here is that it goes like this. Because data, if we think deeper, is input to pipelines, and this data could be really large and unclean, as normally the data are from external sources or even multiple external sources that are not under the team's control. To manage this unknown, a possible solution could be to add data quality tests at key stages of the pipeline. And the aim of this test, you can see the green box over here. You can imagine that these boxes are the quality tests. So the aim of this test are to validate that the data output at every stage is as expected. And if at any stage unexpected data is detected, an alert could go off, providing early feedback to the team. And as well, this problematic data would never reach the data lake and hence never be used for the model training, and thus avoiding the scenario that we saw earlier. Such tests can also be implemented with data quality test frameworks. One example is the Great Expectation test framework.
Thank you, Angeline. So we've covered a lot of things in our presentation, so let's bring it all together. We followed Dana and her team through the journey and ups and downs of the data project, from having a proof of concept to having it running in production with data quality tests and quality gates. From not having the right data engineering groundwork, we learned about how we can use data mesh principles to help us build just the right amount of data platform capability through vertical slicing, simple design. And now that we have a data platform, we talked about the pitfalls that she might face and how agile sensible defaults such as CI, continuous integration, test-driven design, and infra automation and any other kind of automation, how this all can help us to manage the complexity of writing and deploying code. And we've touched on the importance of cross-pollinating these enduring engineering practices by building cross-functional teams and adopting a growth mindset as a team, and also to cross-pollinate these practices through pair programming by owning the code together as a team, not as a data science team or a development team. We are one team owning this product. And finally, we've touched on the importance of data quality, especially in data-powered systems. And so you might be wondering, why do we advocate so much for these practices? And that is because these engineering practices give us 4 things that we all value in a data project. First of all is fast feedback. For example, if you change the line of code, the tests will tell you if it's introduce some regression or not. Through pair programming, for example, instead of doing my machine learning spike or proof of concept for 3 weeks or 2 months, I pair with a developer or data engineer to do this, so that as and when there are suggestions to refactor to a function, to add a unit test, to do this and that, we get the feedback right now, right here, as we are pairing, rather than 3 months later. Repeatability. So this can be in terms of space and also of time. So repeatability in space, whatever works in your SIT, you can be sure to work in later environments, and obviously in production. It can be, once you get this kind of into the habit of doing these things, it can be repeated across your different projects as well. And repeatability in terms of time. So whatever works today, right now, in May 2021, the same tests and more will run 6 months from now. And that automation gives you that repeatability to know that the automation of the tests can be repeatable. But third, right? All of these practices help us to keep things simple, and the opposite of simplicity is complexity. Without test automation, if you want to change a line of code, you suddenly have to take off the complexity of the whole code base, right? Whereas if you had, partitioned or, organized your code, partition that complexity into, right modules and with tests around them. If you were working on one thing, you just need to kind of put your headspace in that one thing. And at the end of everything you're doing, you just run your test suite. It tells you everything is okay. So that keeps things simple for you so that you can solve the problem you want to solve. And some of these practices like refactoring, pair programming, all of them help us have clean code, because again, whether we like it or not, whether we are data scientists or data engineer or developer, we're all writing code, and having kind of maintainable code is kind of the foundation, right? Having it maintainable, having it readable means it's easy to change, and means you can evolve it as you move on. And that is the whole point of all these 4 values, the 4 things that we value. It enables us to be agile, to respond to changes quickly, rather than in a regular cadence, rather than in a kind of stressful way when we try to squeeze because the code is working against us. If we have all these things, then the code starts working for us. We can scale horizontally that way. And finally, to deliver customer value swiftly and safely through these practices. So that's all we have for you today. If you would like to read more about what we've been talking about, these links are here. Don't worry about screenshotting them. We will share them on the Slack channel. And yeah.
Thank you. Thank you very much, David. Thank you, Angeline. Thank you for the wonderful talk. Folks, I just want to say that, thank you for sharing the sensible defaults or practices, whatever you want to call it, with the rest of the folks to overcome those engineering challenges on the data project. And a special thank you for me to explain what data mesh is. I've been keep hearing about data mesh all the time. Up until this point onwards, I didn't know how to articulate it in such a nice way. So thank you for doing that as well.